In previous lectures, we've seen that chlorine is by far the most commonly applied disinfectant for wastewater, or for that matter, for most disinfection applications, and with good reason. Chlorine is very effective for inactivating most bacteria and viruses. It's relatively inexpensive, and the process behavior associated with chlorine-based disinfection is well understood. But we also recognize that there are important limitations of chlorine-based disinfection, including its inability to inactivate some important microbial pathogens, notably some protozoan parasites. There's also problems associated with chlorine that relate to chemistry and toxicology. So there's motivation to consider alternatives to chlorine-based disinfection, and among the most important alternatives to chlorine-based disinfection is a process involving UV or ultraviolet irradiation. UV irradiation accomplishes microbial inactivation following fundamentally different pathways than those that are associated with chemical disinfectants, such as chlorine. So as a first step in addressing UV disinfection, we'll consider what is ultraviolet radiation and what are the fundamental laws that govern photochemistry, the processes we'll be relying on to accomplish microbial inactivation with UV irradiation. First, let's consider the electromagnetic spectrum in a broad sense. So what is electromagnetic radiation? It is energy that propagates through space. It has wave characteristics, meaning that its energy is inversely related to its wavelength. It also has particle characteristics, in that energy is available in discrete units. The smallest discrete unit of electromagnetic radiation is the photon, or the quantum. This leads to what's often been described as the wave-particle duality, meaning that electromagnetic radiation has characteristics of both waves and particles. Visible light represents the range of wavelengths that the human eye can respond to, and it corresponds to wavelengths between about 400 and 700 nanometers. Ultraviolet or UV radiation involves radiation at wavelengths less than 400 nanometers, and in fact there are several subcategories of UV radiation. Those include UVA, which spans the wavelength range from 320 to 400 nanometers, UVB, which spans the wavelength range from 280 to 320 nanometers, and finally UVC, which spans the wavelength range from 200 to 280 nanometers. The focus of our discussion related to UV disinfection, and for that matter most other photochemical processes that are used in water treatment, will involve UVC radiation. So it's important to recognize what that wavelength range is. For completeness, I've also included the definition of vacuum UV. That is radiation that spans the wavelength range from 100 nanometers to 200 nanometers. It generally is not that important with respect to UV disinfection processes, at least those that involve aqueous media, but it's important to recognize that it is part of the spectrum and in fact part of the ultraviolet portion of the electromagnetic spectrum. Now let's get into the laws of photochemistry. These relationships were developed by a group of iconic scientists, and these laws were developed in the 1800s and the early 1900s, so they're very well established. The first law of photochemistry, also known as the Grotius-Draper law, states that radiation, or photons, must be absorbed by a molecule to bring about a photochemical change. The second law of photochemistry, known as the Stark-Einstein law or the photochemical equivalence law, states that for each photon absorbed by a chemical system, only one molecule is activated for a photochemical, or for that matter, for a photophysical process. What does this imply? First, it implies that photons, or quanta, interact with at most one molecule. And in fact, if we consider that a little bit further, an absorbance event is an all or nothing event. Either all of the energy of a photon will be absorbed by a molecule, or none of it will. There is no partial absorption of photon energy. Next, we can consider the definition of Avogadro's number in the context of molecules, atoms, and ions. Specifically, Avogadro's number of these units, the smallest discrete units of chemicals, is defined as 1 mole. There's a similar definition that applies for photons. Specifically, Avogadro's number of photons is defined as 1 Einstein. This gets to the concept of photochemical equivalence. Specifically, molecules and photons are treated as equivalent participants in photochemical reactions. The third law of photochemistry, also known as the Bunsen-Roscoe law or the law of reciprocity, states that the extent of a photochemical reaction will be governed by the dose, or more formally the fluence, of radiation absorbed by that target, independent of the time required to deliver that dose. In other words, if you deliver a dose of radiation to a target over a long period of time, and then in a second experiment you deliver that same dose of radiation to the target in a shorter period of time, the extent of the photochemical reaction will be the same in both cases. It doesn't matter how long it takes to deliver that dose of radiation to the target. There are a number of implications of these laws of photochemistry, and we'll consider some of the most important ones in the next couple of slides. First, a photochemical reaction may take place if and only if radiation, or more specifically photons, of an appropriate wavelength are available to be absorbed by a target. And second, those photons are absorbed by the target molecule. Next, we need to ask, what do we mean by the term appropriate in terms of the radiation? What is meant there is that the photon energy meets or exceeds the energy of the chemical bonds that are going to be broken or formed in the photochemical process. In other words, all of the energy for that process comes from the photon. So the energy associated with the photons that are being absorbed must be sufficient to break or form a new bond. Also, we know that those photons must be absorbed by the target molecule. Next, let's consider what is the energy associated with a photon. That's defined by this relationship, specifically where the photon energy, U sub p, is described as the product of the Planck constant and the frequency of radiation. But the frequency of radiation can be described by the quotient of the speed of light in a vacuum and the wavelength of radiation. We don't often consider individual photons in processes, much in the same way that we don't often consider individual molecules. So it's useful for us to consider larger groupings of these reactants in the context of photochemical processes. So this relationship is useful that allows us to calculate the energy per Einstein at a given wavelength. And that's described by the product of the photon energy, U sub p, which was defined above, and Avogadro's number. Now let's consider photon energy versus bond energy. As mentioned previously, photon energy must meet or exceed bond energy for a photochemical reaction to take place. This is a minimum condition for a photochemical reaction to occur, and we also know that that photon must be absorbed by the target molecule. In this graph, we see a representation on the vertical axis of photon energy and bond energy as a function of wavelength. So what's done on this graph with the red line is to describe that relationship that was illustrated on the previous slide of photon energy or energy per Einstein as a function of wavelength. And we can see this inverse relationship showing up. Superimposed on that are reported values of bond energies for some critical bonds that are common in nature. Also superimposed on this graph are the wavelength ranges for the various types of radiation that were considered previously in this presentation. And we can see that for most of the bonds that are illustrated here, photochemical reactions involve or require radiation from the ultraviolet portion of the spectrum. But that is not to say that visible light doesn't also contribute. In fact, we know that there are some absolutely crucial photochemical reactions that take place involving radiation from the visible portion of the spectrum, notably photosynthesis and human vision, or for that matter, vision for most animals. These are photochemical processes that involve radiation from the visible portion of the spectrum. There are also some somewhat less critical processes that involve radiation from the visible portion of the spectrum, including film photography. Summarizing then, the first and second laws of photochemistry define the minimum conditions that are required for a photochemical reaction to occur. Specifically, the photons must be absorbed by a target, and the photons must have energy that meets or exceeds bond energy. Next, we know that most photochemical reactions of interest are initiated by radiation from the ultraviolet portion of the spectrum. The third law of photochemistry indicates that the extent of a pure photochemical reaction is governed by the dose of radiation delivered to the target. And as we'll see going forward, that tells us that dose is the master variable in governing the extent of a photochemical process, and the time required to deliver that dose does not affect the reaction extent.